Okay, so if we're going to try to get the first side to look like the second side, the first thing I would want to do is split this. Do you see how I have a plus or minus in the numerator but not the denominator? That means I'm allowed to do this. 1 over cosine of x plus sine of x over cosine of x. But we can't get ahead of ourselves. What is the thing that I did? What was that called? What did I call this when we? Splitting. After you do a step, you have to tell me what you did. That's the proof part of this. So you do something, you tell me what it is. And you only do one thing at a time. Now I know some of us see what's coming, but one step at a time. Let's deal with the first fraction. What does 1 over cosine have that would get it to look close to what my goal is? Yeah, if you use the reciprocal identity, 1 over cosine of x is secant of x. So we do that, and then we stop for a second, and we say that we use the reciprocal identity. That's the reason I got to write the next step down. Yes? Okay. What's the next rule that I can use to get it to look like our goal? What? A whole bunch. The quotient rule. So if I change the second fraction by its quotient rule, it becomes tangent of x. So we change it. We say that we use the quotient identity. That's the proof part of it. And once my problem looks like what it told me to get it to look like, so they match, you're going to do this thing at end. It's at end of formal proofs in math. You would use this symbol. It's called the QED symbol, and it's literally a filled-in box. And because we're aiming towards higher level math goals, we're going to get used to using a little box. That is the indicator that says, I'm done. It stands for, in Latin, quod erat demonstratum, which translates to which is what has been proven, basically means the end. So at the end of your proof, after you've told me what to do on each step, you give me the little box and fill it in. Now, if you're like, I need to see that this is actually a 2-column proof, and you like to split your paper like this, between the work and the proofs, you can draw like a little line to show it's a 2-column proof. I've done my work. I have my reasons. Yes? That's a very basic proof. That's kind of along the lines of the ones we did last time. We're going to make them a little bit harder this time because we need to amp it up a bit. So we'll go to question 2. Our goal is to get the left-hand side of this problem to look like the right-hand side of the problem.
We can't do the other way around?
You could, but you want to start with the bigger one and simplify it down to the smaller one. Don't try to like add things to it to make it bigger. Start with the big one, simplify to make it smaller.
So we are doing the first one. I mean, so we are simplifying that one.
Yeah, that's what I said.
Oh, okay, that's fine.
Okay. Does anybody have an idea of where we could start?
We can separate.
Ooh, we can only separate when there's no plus or minus in the denominator. Well, I guess we could separate technically where sine to the 4th of x over the entire denominator minus cosine 4th of x over the entire denominator, but nothing is going to immediately simple there. So, what am I trying to say? Thank you.
What about
Cancel stuff out.
Yeah, we can cancel.
perfect square thing?
Oh, perfect squares. Yes, it's to the power of 4, but this is just the difference of 2 squares. They're just squared squareds because 4 is squared squareds. So if I use the difference of 2 squares factoring, this is going to be sine squared of x minus cosine squared of x times sine squared of x plus cosine squared of x all over that cosine of x minus sine of x. Okay, but before we go on, we have to give a reason we just did that. What is that factoring pattern called? Difference of 2 squares. You can write that all the way out, or you can use the shorthand dots. Difference of 2 squares. We use the special factoring pattern. Actually, let's add the word factoring. That way, if you look back later and you're like, what? Factoring is the difference of 2 squares. All right, what else? What could we do again?
Turn sine squared x plus cosine squared x into 1.
Okay, we can change this right here into 1. What allows us to do that?
Wait, the pi.
The Pythagorean identity. Okay, cool. So that becomes sine squared of x minus cosine squared of x times 1 over cosine of x minus sine of x. Oops, that's too many i's. Now again, we're allowed to do that because of the Pythagorean identity.
Wait, no.
Now again, this can happen in any order, or like you can do these problems differently because I actually did it differently on the notes that I'm going to put online, and that's okay. I'm going to keep going this way because you guys had this idea. What else could I do now? What do we see?
Can you put sine of x minus cosine of x?
If we factor the difference of two squares one more time, this would be sine of x minus cosine of x over cosine, or over, my bad, sine of x plus cosine of x.
Oh my god.
All of that divided by cosine of x minus sine of x.
Oh, that's 1 over.
Hold on, we have to write the reason.
That's that.
Before you get ahead of yourself, what is the reason I could do this? What was that called again? Dots. Difference of two squares. That's a factoring term.
I don't like dots anymore.
Now I see you're thinking of things.
We can do 1 on that one. And then
Which one are you pointing at?
the right one, the top right. And then cancel out the bottom, like, and the top left.
One step.
Okay, so we want to try to cancel out the something in the top and something in the bottom, right? Because I can see they're pretty close. But I need, essentially, now the idea that Nicole had is going to work. I need these signs to switch, don't I? So that these will match these. Do we see that? So what we want to do is we want to multiply the top by -1. It's going to allow just the first parentheses to switch sides. We've essentially factored out a -1, and that's going to be the proof words that we use here.
Wait, why did you flip it for the cosine minus sine? Is that supposed to be right? Or?
Yes, because this is when we're doing the minus multiply by -1 thing. So we can flip them.
Oh.
So the words that you're going to use for this one, for this step when we've been multiplying by -1, the more proper way to talk about it is to factor out a -1. That's the more proper way to talk about that step. We have factored out a -1.
I'm officially run out of space.
You're going to run out of space. What happens now? Maybe if I do this, it'll be even clearer.
Can you cancel each other?
Now these can cancel because everything up on top and bottom has been multiplied or divided. There's no more plus or minus sign in between them. So I can actually do that canceling.
Yeah, I know.
So we do negative, parentheses, sine of x plus cosine of x. So we canceled. That was what we did that step.
Wait. Oh, I thought it was only negative for that. Doesn't it go
Well, that negative doesn't go away.
It won't go away?
No, there's still like a -1 just chilling right there. I didn't cross out the -1. That -1 has to drop down.
What? Okay, so
Then we put a box.
negative.
Ooh, does it look exactly like what is written at the top of the paper?
Yeah.
No,
Oh, well,
Yes.
but
it's the same thing. Oh,
it's the same thing because why?
It's a positive.
Because it's addition. Now I'm just going to erase, I'm not erasing to write anything else. I just ran out of room and I can't draw to the side. So this would be negative sine of x plus cosine of x. And that's because, again, I canceled. So I just rewrote it smaller. The last step would be negative cosine of x plus sine of x. And the reason we did that is called rewrite. The end. You give the little box.
Like a reward.
So you have to get creative. Kind of like you've noticed on the homework, there's not just one method, one algorithm to do this. You have to kind of try different things on these problems. But every time you do something, you tell me a reason.
It's like the exact problem that was on the homework.
It might be.
I'm not rewriting it. I felt this.
Okay, here's number 3.
The only thing was on
What
the
are we
pad,
thinking
you
here?
had U and Gian.
Homework.
It is the homework problem. Let's do it again. Let's see if we can remember what we did, because now we have to prove it. Not only do we do it, We have to prove it.
Above them if you're using this, how small can you write?
So we get them to have the same denominator. Very good. All right, so the first thing we're going to do is give them a common denominator, which means both fractions need both denominators. Meaning the first fraction is going to be multiplied by cosine of x, making it squared. And the second is going to be multiplied by 1 plus sine of x, which means that whole thing is squared. Now, the reason we were able to do that is called least common denominators. And then we put them together into one fraction.
Oh, that's cosine squared.
That step we're going to call combine like terms, because that's what we're doing. We're adding them together. We're combining the like terms together. My next instinct on this one is to multiply out this perfect square, because it's the same thing squared. We would use that pattern to multiply it out. Cosine squared of x, just hold on there in the front, we'll deal with you in a second. The perfect square factor says to multiply the first thing and square it, double the two things multiplied together, so 1 times sine is sine, so we just have 2 sine of x, and then square the second thing.
I have a question. Couldn't you just cancel out one of the signs and just there's another sign and matches on the denominator?
It's very tempting to do that, but this plus sign keeps me from being able to do that. If this cosine squared of x was multiplied by this, yes, 1000% we could have canceled, but we can't because of the plus sign. Now the reason we were able to do this last step is called perfect square factoring or multiplying. Basically, I foiled that. I just did it quick in my head because there's a special pattern for it. Now this next step is kind of an unnecessary step, but I think it's helpful while we're learning. I'm going to rewrite this numerator in a different order. And since I'm showing a step, I have to give it a name. I have to prove what I'm doing. Rewrite. Or reorder. You just reordered the formula. Now, I did this on purpose because what do you now notice is happening right here? Those become 1. What identity allows me to do that? The Pythagorean identity. Okay.
Is it okay if I just like instead of writing the bottom ones over and over, I can just like put K? Like I stored it on K.
No. You can only store numbers anyways. Nope, it is lengthy. You have to write all of it. Okay, the next thing I see is that I have 2 1s on top. What can I do with those? Add them. So I'm going to combine like terms together again and add these. So I do a step, and then I say what I did. That was combine like terms. Yes.
On the homework, are you gonna make us say what we did?
Oh yeah, that's the proof part. I could have gone back and had you prove all the ones on your other homework, Because the problems are the same types of problems. It's just now adding the proof part of it.
Are we all the same problems?
Nope.
Oh.
I know.
Just write the answer and
So I notice
put all the different steps behind it.
that I want to factor out this 2, since both of the terms in the numerator have 2 in them. So I do that, and then I say what I did.
I thought I was drawing small. Writing small.
That feel hurt.
And what happens?
Cancel out.
These now cancel. Now they cancel because there's no more plus or minus in the top between the 2 and the thing I'm wanting to cancel. So I have 2 over cosine of x because I could cancel. And remember, our goal was to get this to look like 2 secant of x. I'm close, but how do I finish it? The reciprocal.
I thought it was smaller.
That's the reciprocal identity, and I'm done. Okay, now I know it's a lot to think about because you have a lot of things going on in one particular problem. But as long as you give me the rule that you use to finish the problem, you are doing it right. Which is what we did this, we modeled this last time because every time I'd say, why did we do that? And you'd tell me what identity we used. It's the same thing, you're just writing it down. And then the problems got more complicated. Let's see number 4.
No, no more.
We can do it. We can do it. On number 4, our goal is to get this side to look like this.
What?
We can't split this one like we did the first problem because the plus or minus is on the bottom.
Does the bottom become cosine squared? No, there's no square.
There's no squared, so it doesn't. Wouldn't that be nice if it did?
Yeah, I just noticed.
To finish regular cosine?
So what we're going to do, it's the first example where we've seen this. We're going to take this and we're going to multiply by its conjugate.
I don't remember that. I'm remembering smaller.
So we're multiplying by the conjugate, which is just the opposite of the denominators. And what happens is the bottom is now a difference of 2 squares problem, which means the denominator multiplies out to 1 squared, which is 1, minus sine squared. This is why it's going to be super important to recognize difference of 2 squares pattern. The numerator, it just looks like this. We have cosine of x and we're multiplying it by 1 plus sine of x. So that is the difference of 2 squares.
It's small time. It's small time.
What is your next idea? What are you thinking?
Cancel?
No, nothing cancels.
Power on trying to make it right smaller. Actually.
It was all of your first instinct probably because then you noticed there was no square when we started.
Turn it to cosine.
Yeah, what can we change the bottom to?
Cosine.
Cosine squared of x. What is the reason I'm allowed to do that?
Because it's squared now. Oh, fine.
The Pythagorean identity.
I'm wrong.
Now do we cancel?
Now do we what?
Now do we cancel?
We do. What are we canceling?
Cosine.
Cosine and one of the ones that's squared on the bottom. So our next line of this problem looks like this. 1 plus sine of x over cosine of x. That was a cancel step. Now think about our goal. Look at the goal that we want to finish with. What do you notice about the goal we want to finish with?
Secant squared x plus tan of x.
There's 2 parts, so we need to split it apart so it can end up looking like our goal. So because the plus is in the numerator, I'm now allowed to split these two fractions basically by their common denominator. That's a split step. I wasn't allowed to do this earlier because the plus or minus was in the bottom. I can only do that when it's in the top. And again, I know you can kind of see it coming, but we do one step at a time in a proof. Let's take care of the first fraction. Can we get it to look like the goal? Yeah, the reciprocal of cosine is secant, so we can go ahead and change that. Again, one step at a time. That is your reciprocal identity. And we're almost there. What's the last thing? The quotient identity allows me to change the second fraction to tangent. And once they match with the goal, and you've given me the last reason, you get the little box that says the end. QED. We just have to get creative. That's the bottom line.
God, I can already tell.
Do this assignment in pencil because you will erase.
Do it in pencil.
I also erased when I was doing it.
Oh.
And then obviously did some way harder than I needed to. So I probably could have stopped and gone back a little bit. Yeah, don't do that. Okay, last one with me. But y'all are going to drive this ship. You're telling me what to write.
Ooh, make it cotangent into cosine of cosine.
1/10.
Okay, so we're going to, I heard make cotangent into what?
Is this sine? No, it's cosine over sine.
Okay, so we're going to make the cotangent into cosine over sine. What allows me to do that? What?
Yeah.
What is it called? The quotient identity.
Not one.
That's on the front of your formula chart if you're looking for it. The reciprocals and the quotients are on the front bottom. Okay, what next?
Yeah. No. You can't cancel.
Can't cancel yet.
Like,
Can you turn tangent into sine over cosine?
We totally can, because remember, tip number 10 on the help to prove things page of this note said when all else fails, turn it into sine and cosine. So that's what we're going to do. If we use the quotient identity again, tangent becomes sine of x over cosine of x. Cool. That's the quotient identity. What next?
I have no idea.
Look at our goal. Does our goal have a plus or a minus in it?
Neither.
No, so there's going to be some way that we have to combine these together so we get rid of the plus or minus. Ooh, cross multiplying? No, that happens across equal signs. Make the denominator the same. That's a good way to get it to go together. So if we make the denominator the same, both denominators need to be sine x, cosine x. Which means the first parentheses is missing what? Sine. So I'm going to just square the top so that it is multiplied by another sign. What is the second one missing? Cosine. So I'm going to square that cosine since I multiplied it by another cosine. This is the least common denominator step. Then we just need to add our two fractions together into one fraction. That is our CLT. We're just adding these two things together, combining the things.
Does it turn to one?
Ooh, what turns to 1?
The top.
The numerator. Why is it turned to 1? What's it called? The Pythagorean identity changes the top to a nice looking 1. It's starting to get simpler.
Then can't you separate them?
We can separate them. So we're going to take these two fractions, and instead of multiplying them together and making them look like the way I have it written, I'm going to separate it like this, just to visually see them different.
We have to do it one by one.
We do have to do it one by one because the rules are with proofs, you do one thing at a time. I,
Do this in college?
huh?
You want to prove this in college?
Depends on what class you take.
What class?
I know y'all can see it coming. I know you see what the ending is here. But one at a time, 1 over sine
Turn into secant.
turns, well, 1 over sine turns into
Oh,
cosecant of x.
SS, they're very confusing.
That's the reciprocal identity. And then 1 over cosine changes into secant from the reciprocal identity. And if we're really being sticklers for proofs, that doesn't exactly match what was on the paper. So what do we need to do? Oh my gosh. Rewrite it. Which I know feels like just extra, but if we're being sticklers for proofs, depending on the level of math you're in, you may have to prove that you can rewrite it.
Count up points, not it being the right way.
I've had professors do it, so potentially yes. And I've had other professors that don't care, but
Have beef with
just depends on your prof.
It's like those types of teachers, it's like, prove this is a triangle.
So
Correct.
I have to find
Is it?
the third one.
You can't say it just looks like a triangle.
I mean, this looks like a triangle.
Tables.
Can't prove it yet. It's actually not a triangle because of the curved edges.
Well,
What shape is this?
That's a rhombus.
I actually don't know. I don't know the proper name for it.
it's a shape.
It's a shape. Okay. And that's proofs. Basically what we did last time with an explanation for each problem. These problems are just a teeny bit harder.